Okay, so now we have, this is possibly the last topic of this course, also very important topic in the subject of constraint optimization. Many of you may have come across these terms as you've been reading papers. So this is the connection between KKT and what is called duality. Okay, so that's what we're going to explore now. KKT and this is of special significance in convex optimization, which is why a course on convex optimization would spend a lot of time on it. By the end of doing this topic, you will see why it is not as much of importance in non-convex optimization, but it's still a very important and useful concept if we want to bound things. Okay. So following our general approach, rather than start with some dry definition, we'll take some problem, work out some geometry and get some intuition before formalizing any theorem over here. Okay. So we'll take a problem, we will solve it the way that we have usually been solving it. We'll come up to some solution, right? Then I'm going to introduce an alternate way of solving this problem, which is called duality. Okay. So that's the general strategy. So let's take an example. I'm going to take an objective function which is actually quadratic. Okay, this is my function. And problem 1 is I want to minimize this. Okay. So as before, I've taken a simple enough problem that we can visualize the problem and the solution in one shot, right? So what is this, what are the contours of this cost function? Circular in the x1, x2 plane. So if I take this as x1, x2, these are like this, right? And they are increasing outwards. So in 3D, this is like a bowl, right? It's a parabolic equation. What is my feasible region? What kind of space is it called? It's a half space, x1 plus x2 greater than 2, right? So it's a line that cuts both x1 axis, x1 and x2 axis at what value? 2, right? So it's going to be something like, and should I be to the top or the bottom of it? Top, right? This is the feasible region. And we already know the solution to this. What is the solution? That circle which is tangent to this blue line, and it's going to be basically this point over here, right? So this true solution, can you guess the coordinates? 1, 1, right? Okay. So it's nice to have a really simple problem because you can follow along the algebra very well. So if we were solving this problem using our KKT business, what would we do? First step would be to form the Lagrangian, right? So Lagrangian x comma lambda will be what? Fx minus lambda cx. I just have one constraint, okay? As per KKT theorem, what would I do next? Take the gradient of the Lagrangian, okay? So grad f minus lambda grad c, and I'm going to set this equal to 0, right? What else does KKT tell me? Any condition on lambda? Lambda should be greater than or equal to 0 because it's an inequality, not an equality. Right? So lambda should be greater than or equal to 0. This is due to inequality. If it were equality, there is no constraint. Lambda can be positive or negative. And complementarity will tell me what is the complementarity condition? Lambda into c x is equal to 0. This is basically what KKT theorem tells us. So if I take the first gradient expression, grad f is going to be what? What is grad f? 4 by 5 x1 x2, right. So this is 4 by 5 x1 x2, okay, minus what is grad c? 1 1, okay. Okay, so this is what we get. Of course, this is not good enough by itself, because I can take any value of lambda, I can take substitute, I will get some value of x1 x2, right. So for example, if I take lambda equal to 1, what do I get? I get x1 x2 is equal to 5 by 4 comma 5 by 4, right. Is this fine? On the face of it, it looks okay or no? No. What's wrong with it? Correct. But over here, if you look at c of x, it is not equal to 0. But complementarity insists that c of x should be 0, because lambda is non-zero, right. So this is not a good solution, right. I mean, you can play around a little bit more. You can see that if lambda is equal to, for example, 4 by 5, what do I get for x1 x2? 1 1, and at this point c of x is 0, right. So first order KKT conditions are satisfied. We've got our solution, okay. All right, so now this was the standard way of solving this problem. Let's see if we can solve this differently, okay. So now I need to add a page, okay, okay. I'm going to do this in 2 steps. It's like I'm giving you a 2-step recipe. So we'll just blindly follow the recipe to start with and see what it gives us, okay. Step 1, I'm going to define what is called a Lagrangian dual function. So it's called Lagrangian dual function, okay. It's defined as q of lambda. So remember, it's a function of lambda, and the way I define it is I minimize over x the Lagrangian, okay. Keep in mind our Lagrangian was f of x minus in general, right? That's our Lagrangian. So what is the first step is you form this Lagrangian dual function and keeping lambda fixed, minimize this with respect to x. So for every different lambda, I'm going to get something else, right. For every different lambda, this minimize the Lagrangian with respect to x will give me some different expression, right, because that's how it is, okay. So let's try to solve this problem. So it's a sub problem in step 1 which I have to solve. So let's go back to our example. So what was our Lagrangian over here? So if I want to minimize Lagrangian with respect to x, what would I do? This is constraint, I mean this is almost like unconstrained optimization to start with. So I would put the gradient to 0, right. So this is what I would do. Okay. And we have already done this precise thing, so which I'm going to just write this over here. This is what I would get by setting the Lagrangian gradient to be 0, okay. Now notice that this Lagrangian dual is a function of lambda, which means what? I should eliminate x1 x2 from here, right. So from here I can basically write x1 is equal to lambda by 4, sorry 5 lambda by 4, x2 is equal to 5 lambda by 4, and I can substitute this back into my Lagrangian expression, right. So what would I do? So let's call this x star, x1 star, x2 star. Why am I writing this as x1 star, x2 star? Because this is the x1 x2 under which gradient of Lagrangian goes to 0, therefore this expression is minimized, right. So q of lambda, so q of lambda is going to be the min part I don't need to write because I've already done it. I'm left with Lagrangian, right. So Lagrangian is f of x, so 2 by 5 x1 squared x2 squared minus lambda x1 x2 star minus 2. This was my q of lambda with the optimum x. The x which minimized it is what I have put in over here, right. That is how I got rid of the min. Everyone with me on this? I got rid of the min by replacing the actual min, that is why it is a x1 star, not any x. It is that x which minimizes the Lagrangian, right. And I am going to substitute this. What kind of a function do you expect I will get in lambda? Trigonometric, exponential, quadratic? Looks like a quadratic, right? You can see because x1 is basically 5 by 4 lambda. So, right, so this is going to be 4 by 5, x1 is equal to x2, so that is how I am going to get a 2 and 5 lambda by 4 whole squared minus lambda 10 lambda by 4 minus 2, okay, and so there is going to be minus 5 by 4 lambda squared plus 2 lambda, okay. Before we go further, everyone agrees with this or is there a typo somewhere? Right, this is fine. Just out of curiosity, what is the shape of this cube? It's a downward parabola. What is our immediate hint that we didn't even have to graph it? Its origin is okay, but origin I can have upward opening parabola also. When I take the what? The second derivative, the only one term is going to survive, which is the lambda squared term, and it has a negative value, it's negative curvature. So this is a concave function, right? It passes through the origin and one more point. So and it's downward opening. Okay, so we'll just make a note. This is concave. We'll come back to this later. Okay. So this was step 1. Take the Lagrangian, minimize it with respect to x. So I am left with a function in lambda. Now step 2 is find the lambda, okay, which is greater than or equal to 0, which maximizes q of lambda. Okay. So more formally, this is max over lambda q of lambda such that lambda greater than or equal to 0. Okay. Does it make sense for me to maximize a concave function? It makes perfect sense, right? In fact, minimizing a concave function would be disastrous. So this is well defined. So to maximize this function, what can I do? I can differentiate it. Even for a maxima, the derivative should be 0, right? So I can take derivative. Here I don't have to take gradient, right? A derivative is enough because it's a scalar function, right? So what will I get? Minus 10 by 4 lambda plus 2 is equal to 0. This gives me what? Lambda star. Now this is a special star, right? This is the star that maximizes q of lambda. Lambda star is going to be equal to what? 4 by 5. Okay, and I have this relation over here for x1 and x2. So when I substitute it back, I get x1 star is equal to x2 star is equal to 5 by 4 into 4 by 5, which is equal to 1. Right? Which is the same solution as we had in the regular approach, right? So the so-called regular approach, which we did over here, taking the KKT and setting the derivative equal to 0, blah blah blah. This is what is called as it's not called the regular approach, it's called the primal approach. Okay, and what we just did right now in this two-step formula is what is called as the dual approach. Okay. So let's just summarize this because this is very important. So So we can call it the primal approach, or we can call it the primal problem. So the primal problem is what we have been solving in this entire course, right, which is minimize f of x, where x is a variable, such that c of x is greater than equal to 0. This is what we have been doing the entire course. So for the primal problem, there is now a dual problem, for which I have just given you a recipe without any intuition, without any proof, but we will work on that. So the dual problem is in 2 steps. The first step is form the Lagrangian dual. So how do I do that? So I called, let me write it like this. So Q of lambda is minimize over x, the Lagrangian, okay. And then once I got this, what did I do? I maximized the, right. So maximize the Lagrangian dual function, okay. Now this remember, this lambda greater than equal to 0 comes for the inequalities only, right. So let us write this as I. So whichever problem has any set of inequalities, those are the Lagrange multipliers which have to be kept non-negative, okay. So this is the so-called dual problem. Okay. Now you can see that in the example that we took, the primal problem and the dual problem give the same solution, 1, 1, right. So which approach should you take? It's not at all clear, right. So this switching between 2 approaches, as it turns out, in the world of convex functions, if your function is convex, if your constraints are convex, both of them give the same solution. So this is a very big result, right. So let's just note it down. For convex problems, both give okay. And in many problems, it turns out that the dual problem is easier to solve than the primal problem. In our toy problem, both were just the same difficulty, so you can't see it. But when you come to more complicated problems, you will find that the dual problem is often much simpler to solve. So dual is, so I'll just make a qualified statement, generally easier to solve, and I'll in subsequent we'll talk about why it is easier to solve. Okay, so this gives us a new and powerful technique of solving convex problems. The original problem, the primal problem, is hard to solve. Formulate the dual, solve the dual. Dual is often supposed to be simpler. Okay, getting a little bit ahead of myself, for non-convex problems, the solution to the primal and the solution to the dual is not the same. So you will come across this expression in the literature, strong duality and weak duality. So when the 2 problems give the same solution, it is called strong duality. When the 2 do not give the same solution, it is called weak duality. And the gap between the primal solution and the dual solution is called the duality gap. So you will come across these words many times. Okay, so I'll talk about it subsequently as well. But this is the basic sort of setup of a new technique of solving your original problem. Okay, as the way that we have done it, it really, there's not much intuition that anyone could get. It's like I gave you a recipe, we did this blindly, and we got the solution. What is the intuition behind it? What is the proof behind it? That did not come out. So what we'll do is, again, rather than giving you a grungy algebraic proof, we'll sketch some diagrams so that we get some intuition. We'll prove that later. We'll prove it. We'll come to it. So before we get into proofs and properties, I want to give a geometric intuition, and then we'll prove that Q is concave. It's not very tough. Okay, so we're going to sort of give geometric intuition as to why this two-step process of the dual problem actually worked. On the face of it, it's not at all clear why it should work. So I have my f of x, just want to use the same problem, x1 squared plus x2 squared, and I had my c of x was x1 plus x2 minus 2, and I wanted this greater than equal to 0. Okay, and this is my x1, this is my x2, right? So the feasible region over here was this. Everyone agrees, right? Now, what I'm going to do is, I'm going to create a map. We're going to go from the x1, x2 coordinates to another set of coordinates. I'm going to call them y and z, okay? And how do I define this y and z? I'm going to define y and z in a very simple way. So y is going to be equal to c of x, z is going to be equal to f of x. Okay. I can do all of these tricks only in a problem of two variables, otherwise it will be impossible to sketch this. So I have y and z. Okay. So let's proceed. It's and this map, right? This is a map. I'm going from the x system to the yz system. Yeah, because it's not a very straightforward map, because f is quadratic, c is linear. It's not that every point is going to get mapped to a point one to one kind of a thing, right? So let's proceed step by step. So let's look at the feasible region. The feasible region on the left hand side is the blue shaded part. Everyone agrees, right? That is quite clear. In the new map, YZ map, where is the feasible region? Everything on the right hand side, because y is c of x and c of x should always be greater than or equal to 0. So y greater than 0 is the right half plane, right? So the feasible region first of all got mapped over here. Okay. Then what do I have? This is not enough, obviously. I need to also figure out how, what are the contours of the function, etc. Right? So let's start that analysis. For example, let me consider a line x2 is equal to a. Okay. So let's try to see that if I take a line in the x1, x2, what does it get mapped to? Right? There are various ways of getting this mapping. This turns out to be a simple way. So if I take x2 equal to a as a line, and I now need to get some relation between y and z, then that will tell me a line in the x plane got mapped to blah blah in the yz plane. Okay, so I need a relation between between y and z. So let's proceed with that. So y is equal to x1 plus x2 minus 2, right? What is the value of x2? A. So this will become x1 plus a minus 2. What is my z? 2 by 5 x1 square plus x2 squared, right? Which is equal to 2 by 5 x1 squared plus a squared. From these two equations, is it possible for me to somehow eliminate? I want a relation between y and z, so that I can make a graph in the yz plane. How would I do that? Substitute, right? I basically eliminate x1. So I can take x1 and write it in terms of y and a and put this into the second equation. So you would get z is equal to 2 by 5, and I would write x1, which is nothing but y minus a plus 2 whole square. This is 2, and I have a plus a squared, right? So this is what I wanted, right? Because a is a number, and now I have a relation between y and z. What does this relation look like? What kind of a graph is this? It's a parabola, right? For different values of a, what is changing in the parabola? right? The lowest point of the parabola is shifting. Anything else that is shifting? The offset is also changing, right? If I take this plus a squared on the right hand side, if I take it to the left, I will have, I mean the classic equation of a parabola, it will look like this, right? Z minus 2 by 5 a squared is equal to 2 by 5 y minus a minus 2 whole squared. So when I plug in different values of a, z minus some positive quantity, right? The parabola is shifting up or down? It's always shifting up. For every time I put z equal to 2 by 5 a squared, I'm going to get 0 there, and therefore I can choose, basically I can get that point, right? So I have these parabolas that are always, I mean they're always increasing. So okay, let's take a simple value, a equal to 0. What is the equation of my parabola? Z is equal to 2 by 5 what? Y plus 2 whole squared. So this is a parabola which is, where is the center of it, or rather the lowest point of it? Minus 2 comma 0, right? So you can substitute, right? When I put y equal to minus 2, what is the value of z? 0, right? So this parabola actually looks like this. Everyone agrees? This one line x equal to a has been mapped to one parabola, right? So it's not such a straightforward transformation also, but it's mapped over here. Now when I substitute different values of a, we know that this parabola can never shift below. It's always going to shift up. So it's shifting up, but along with shifting up, it's also shifting which way? Right side or left side, depending on a, right? The center is a minus 2, right? So a minus 2 can float around this way. But the point is it always stays above, right? So when you do this exercise, it turns out that the entire, for all possible values of a, when you look at what all are the different possible parabolas, you would map the entire x1, x2 region into some region on the right hand side, okay? So you can take my word for it that that entire region ends up being, all of the parabolas somehow they are contained within this one parabola. You can sketch it and see, it's not so obvious, but I'm just take it on faith. So that's why I was at least showing you that the parabola never goes down. The center of the offset is always positive. So even if I give a negative a, it's a squared by a squared into 2 by 5. It's always staying up there. So okay, so this is what the map looks like. Okay. Okay, so now let's, the geometry, is everyone clear with the geometry? Little bit you are taking on faith that everything is contained inside this upward bowl. Okay, intuitively it makes sense. Okay, so now I'm going to ask you a question that is pure geometry. Okay, so I'm going to, pardon me? A equal to this guy. This is minus 2 comma 0. You agree that this is, right, at minus 2 comma 0 passes through this equation, right? Y equal to minus 2, z equal to 0. So that's the bottom point, and then it opens up, positive curvature. Correct, because as I slide a, it also moves up, right? So all of these parabolas end up being sort of contained within this. Yeah, intuitively, yeah, because there's a squared there. Okay.